Welcome to our next lecture of the classical mechanics. In the last few lectures, we have already seen what is the properties of the particles which are moving according to the Newton's law of motion. We have seen the system of particle. Then we have also seen the very important concept that is constant. Then we have seen the holonomic and non-holonomic constant. And then we have seen the virtual work and virtual displacement. Then we have seen the generalized coordinates q1, q2, q3, q4 and so on. And then we have also seen the most important article, that is the transformation equation. Today, the remaining few articles of this particular chapter of the classical mechanics that we are going to consider here. Let me share my screen first. We found that in this lecture, first of all, we will see about the D'Alembert's principle. Then we will go for the Lagrangian equation. Then we will see the simple application of the Lagrangian formulation to the simple pendulum. And then I will summarize the lecture. Now, what is the D'Alembert's principle? In order to consider the D'Alembert's principle, let's go to the Newton's second law of motion, which acts on the particle of a system, and that particle is the ith particle, and it is according to the Newton's second law, it is given by F is equals to ma. But ma, it can be written as Fi is equals to dpi by dt. That means rate of change of momentum with respect to t. And it is the derivative of pi, that is momentum. Therefore, we can write this dpi by dt as pi dot. That is the first derivative of momentum. And if it is so, then this equation may be written as Fi minus pi dot is equals to 0, where I is equals to 1, 2, 3 to n. And this equation, when it is coming as Fi minus pi dot is equal to 0, means any particle in the system is in equilibrium under a force which is equal to the force Fi dash plus a reversed effective force pi dot. And therefore, the virtual displacement delta Ri, it may be given by this equation. Summation I goes from n to n Fi pi dot delta Ri is equals to 0. But from the previous equation, we know that the force acting on the ith particle, it is sum of the actual force acting on it and the force of constraint. And that's why Fi is equals to Fia plus Fi. And therefore, instead of Fi, if I put this equation in this summation sign, then it is summation I goes from n to n F of A minus pi dot delta R plus summation I goes from n to n Fi, small fi of course, delta R is equals to 0. But we restrict ourselves to a system for which the virtual work of the constant is 0. That means on this ith particle, virtual work is 0. That means the force of constant is not working. That means this summation, in this equation, summation I goes from 1 to n Fi delta R is equal to 0 in this equation. And therefore, the total equation will now become summation I goes from 1 to n Fia minus pi dot delta R is equals to 0. And this is nothing but this is the D'Alembert's principle. But we also know that the constant do not appear in the equation. That means the force of constant is not happening to the particle. Therefore, as delta, if force of constant is not working, that means summation I goes from 1 to n delta Fr is equals to 0. That means in this equation, that means in this D'Alembert's principle, instead of writing Fi of A, that means the actual force acting on the particle is need not be here. That means we can remove the superscript A, and finally we can write this equation summation I goes from 1 to n Fi minus pi dot delta R is equals to 0. And this equation is nothing but it is the final form of D'Alembert's principle. So this D'Alembert principle we have derived from the idea of, or from the principle of virtual work of the constraint. And now, after having seen the D'Alembert's principle, the most important article that we are going to see here today is the Lagrangian equation. As I have told you in our last few periods, that according to the Newton's law of motion, when the particle when a single particle or a system of particle it is moving, then for this system of particles, the scientists Lagrangian have derived an equation by considering the basic ideas of Newton in order to specify the motion of particle in a system of particle. And that equation which was derived by the Lagrangian, it is called as the Lagrangian equation. And to derive this Lagrangian equation, scientist Lagrangian has taken the use of Newton's law of motion. He has taken the use of transformation equation. He has taken the use of generalized coordinate. He has taken the use of virtual work. He has taken the use of D'Alembert's principle, which just we have seen here. And that's why let us consider that there is a system of n particle. And if there is a system of n particle, then it is the function of the time coordinates and the generalized coordinates, such as transformation equation will be given as r is equals to q1, q2, q3 of qk, q2, t. That means a generalized coordinates. Where t is the time and qk, that is 1, 2, 3, these are nothing but these are the generalized coordinates. Now differentiating equation 1 with respect to t. For the ith particle, we will get the velocity, because Ri it is the displacement, and therefore dRi by dt, if we take the derivative, then it is come as dou Ri by dou q1 in dq1 by dt plus dou Ri by dou q2 dq by dt and so on. That is dou Ri plus dou t, and therefore final equation we can write as the velocity Vi is equals to Ri dot. That means the rate of change or displacement of the ith particle is equals to, this can be summarized as summation k goes from n to n dou Ri by dou qk dot plus dou Ri by dou t. This is equation number 2. But we know the qk dot are the generalized velocity. Therefore, according to the virtual displacement delta Ri, it may be written as dou Ri by dou qq1 into dou qq1 plus dou Ri by dou q2 plus into dou q2 plus so on. In this way, we can write in general delta Ri, it should be equal to summation k goes from 1 to n dou Ri by dou qk into dou qk. This is equation number 3. Since by the definition of virtual displacement do not depends on time, and just we have seen the D'Alembert's principle, that is summation I goes from n to n fi minus pi dot delta Ri is equals to 0. Therefore, we can write the above equation summation I goes from n to n fi delta Ri is equals to summation I goes from n to n fi, again summation k1 goes from 1 to n, it is dou Ri by dou qk into delta qk. It will be equal to double summation k and 1 from n to n fi dou Ri by dou qk into dou qk, and generalized coordinates are there. Therefore, I can summarize this double summation into 1, that is summation k goes 1 to n gk into delta qk, where gk is the generalized coordinates, and it is due to this equation number 6, that is gk is equals to summation I goes from n to n fi dou Ri by dou qk, means this entire components I goes from n to n f dxi dou xi by dou qk plus f by I dou yi by dou qk plus fzi dou z by dou qk, and so on. And these fx, fi, fz are nothing but these are the coordinates of generalized associated with the generalized coordinates qkk, and this may be mentioned as the dimension of the generalized coordinate need not be those of the length. And similarly, the generalized force component gk may have the different dimension, and those dimension you can also be put, however, for the jq delta qk and so on. And therefore we know summation I goes from n to n pr delta Ri, it is can be given as summation I goes from 1 to n m I Ri into summation k goes from 1 to n dou Ri by dou qq into delta qk. And when I take this 2 into one side in one summation, summation k goes from k to 1, k is equal to 1 to n, summation I goes from 1 to n, this is mi Ri, and derivative of this one is dou Ri by dou qk into delta qk. And therefore summation once again derivative of this one's mi ri derivative to ri double dot, that is derivative of ri dot, it is dou ri by dou qk, it will be written in this manner. This is equation number 8. And we can prove this one by d dt of dou ri by dou qk is equals to minus dou qk of dri by dtt. It is equal to dou vi by dou qk. This is equation number 2, and therefore this equation number 9, it may be written in this manner as equation number 10. But we know summation I goes from n to n, mi ri double dot, this equation dou ri by dou qk is equals to summation I goes from n to n d dt of this one, that is mi vi dou vi by dou qk minus mi vi dou vi by dou qk. This is equation number 11, and you found that the bracketed quantity in this equation number 11, that means this one is nothing but it is the kinetic energy, and it is can be written once again the above equation 11 as summation goes from k to 1 to n d dt of dou by dou qk, and summation of I goes from 1 to n 1 half mi, and vi as it is, there is another vi minus d dou qk summation I goes from n to n 1 half mi vi. That means this bracketed quantity carries the kinetic energy, and this kinetic energy can be denoted by the symbol T, and their above equation may be simplified as summation goes from 1 to n d dt of this entire quantity as a T, therefore dou T by dou qk minus this one dou T by dou qk, and entire is delta qk. This is equation number 12. And in this equation, d dt of dou ri by dou qk is should be equal to summation goes from j to I, that is dou 2 ri by dou qj into dou qk qj dot plus dou 2 ri by dou t into dou qk. This is equation number 13, which has been obtained by treating delta qk by this delta ri upon delta qk as a single quantity being the function of generalized coordinates qj and in time t, but with the velocity which we can write in this manner as vi is equals to dri by dt, summation goes from j 1 is equals to n dou ri by dou qz dou qk qj dot plus dou ri by dou t, and this is nothing but this is the partial derivative with respect to qk, and therefore above equation can be simplified in this one, and therefore it will take the form of equation number 14. And from equation 13 and 14, we found that d dt of dou ri by dou qk is equals to dou v by dou qk, and therefore we can write the equation number 13 and 14 in this manner, and therefore dou vi by dou qk dot is equals to dou qk by dot into dri by dt. It must be equal to dou by dou qk dot, that is of summation j goes from n to n dou ri by dou qj dot plus dou ri by dou t. It must be equal to dou ri by dou qj into delta jk, and that is equals to dou ri by dou qkz. But we know delta z is nothing but it is the holonomic constant. Therefore equation 15 will take the part of this one. We will put summation I goes from 1 to n and delta fi delta ri from equation 6. This summation I goes from 1 to n pi dot delta ri from equation number 12. It is from the D'Alembert's principle, of course, from the equation number 4 previously, and therefore above equation number 15 will take this form. But the bracketed quantity, it can be again simplified that it is a summation and derivative d dt of dou t by dou qk dot minus dou tt by dou qk is equals to 0. Or you may write for the generalized coordinate d dt of dou t by dou qk dot in minus dou t by dou qk is should be equal to jk, where it is a finite. Here this equation number 16 has come because we have seen that this is the holonomic constant, and for the condition for the holonomic constant is that the function of fx or a, it should be the finite one, and therefore this is the equation number 16 is the generalized equation or the general form of the Lagrangian equation, which is used to specify the position of the moving particle. But we know for the conservative system, the force is the derivable force, scalar potential. That means we use the potential energy function, and therefore using the Fi as a delta Vi, that is derivative of the potential energy. And when we will go to the vector quantity, that is I, where it is I, J, and K are the unit vectors. Therefore, Fi delta Vi, it may be written as I dou v by dou xi plus j dou v y by dou yi plus k dou v by dou zi, and therefore equation number 6, the generalized force components, in this case that is jk, generalized components, that may be written as summation I goes from n to n fi dou ri by dou q, and therefore from above equation it is summation goes from I goes from n to n dou v by dou xi, that is dou xi by dou qk plus dou v I by dou I yi into dou I by dou qk, and similarly for the z components. Clearly, the right hand side of the above equation is nothing but is the partial derivative of minus potential, that is minus v, and therefore the general equation can be written as jk is equals to minus dou v by dou qk, and therefore equation above may be written as d dt of dou 2 by dou qk dot minus dou t by dou qk, it should be equal to minus dou v by dou qk, or it may be simplified by taking this quantity to the left hand side, and therefore d dt of dou 2k by dou qk dot minus dou t of t minus v into dou qk is equals to 0. This bracketed quantity is nothing but it is the difference of kinetic and potential energy, and therefore this it may be written in this manner for the equation number 19, or I may put t minus v is equals to L. That means L is nothing but it is the Lagrangian function, and Lagrangian function is nothing but it is the difference of kinetic and potential energy. If I put L is equals to t minus 1, then equation 19 will take this form, that is d dt of dou L by dou qk dot minus dou L by dou qk is equals to 0, and this is equation nothing but it is the Lagrangian equation for the conservative system, and this is the equation which we'll use to specify for the position of a moving particle. And this Lagrangian equation can be taken, can be applied to for the different phenomenon of the motion of the particle. One of the simple application of the Lagrangian equation is to the simple pendulum. As we know from our previous knowledge, that simple pendulum is nothing but it is a thread which is suspended to the rigid support. The length of the thread is small l, and when one second to the other end of the thread, the bob is attached, and when the simple pendulum is at rest, then that position is mean position. When bob is taken in our hand, displaced through some distance and moves to A, and then left, we found that the pendulum moves on the both side of the mean position. And from our previous knowledge, we have already familiar that the motion of the simple pendulum, it is the simple harmonic motion, and the simple harmonic motion equation was given by the differential equation, that is d2 theta by dt square plus omega square theta is equals to 0. If any motion obey that equation, or for the motion of any particle, if that's such type of equation we are getting, then we conclude that the motion of that particular particle, it is the simple harmonic motion. Now in this equation, or in this case, we will apply the Lagrangian equation to the motion of the simple pendulum, and we will try to obtain the equation of motion. So let us consider that theta is the angular displacement of the simple pendulum from the equilibrium position. L is the length, effective length of the pendulum, of course. M is the mass of the bob which is attached to the other end of the pendulum. Then according to one, when the bob is displaced from O to A, that is, this one is the displacement, as you can see on my cursor is going from O to A, that is S, and therefore OA is equals to S, and therefore above equation according to the Pythagoras theorem will become S is equal to L theta, as theta is equals to arc upon radius. Here arc is S, radius is L, and therefore T, that is the kinetic energy, as we know, it is 1/2 mv square, and therefore this equation should be equal to 1/2 m L square into theta dot square. How did theta dot square will come? Because we know V, that is the velocity, is the rate of change of displacement, that is ds by dt. But S is nothing but from this equation, it is L theta. Therefore, d dt of L theta, and when we'll take the derivative ds by d theta, that means velocity will come as L theta dot, and therefore when this L theta dot I put in place of v square, I will get 1/2 ml square into theta dot square. And that means if the potential energy of the system when the bob is at 0, that means at O position is 0, and then when the potential energy when the bob is in the extreme position, that is at A, it will be given by V, and V is equals to mg ob, where mg ob is nothing but it is OC minus BC, and therefore mg as it is OC is L once again, that is length of the pendulum, that is radius, minus BC, it is the component of the cos component of the force which is acting on this is L minus cos theta, and therefore this mg L 1 minus cos theta, L coming common, and it is out of bracket, and therefore the Lagrangian function L t minus v, if I put here, then it is L is equals to 1/2 L L square theta dot square minus v, it is mg L minus into 1 minus cos theta. When I simplify this one, that is dou L by dou theta, if I take here, it is minus mg L sin theta, but dl by d theta is equals to ml square into theta dot, and therefore when I put this, substitute these values in the Lagrangian equation, here there is only one generalized coordinates, particularly q is equals to theta here. Therefore the Lagrangian equation will take the form d dt of dou L by dou theta dot minus dou L by dou theta is equals to 0. And when I take the derivative of this one as d dt of ml square theta dot plus mgl minus sin theta is equals to 0, and where derivative of this one is ml square into theta double dot plus mgl sin theta, as it is when theta is very small, sin theta is approximately equal to theta. Therefore this equation ml theta dot square plus mgl sin theta will take this form, theta double dot plus g upon l sin theta. And this equation, if you remember, theta double dot means the second derivative d2 theta by dt square plus g upon l sin theta. That means this is nothing but it is the differential form of the simple harmonic motion, and that's why from this one we conclude that the simple pendulum perform the simple harmonic motion, and this we have derived from the Lagrangian equation. And if the motion of the simple pendulum is the simple harmonic in nature, then its time period, as you know, it will be given by t is equals to 2 pi under root L upon g. Now this differential equation theta double dot plus g upon L into theta, which we have obtained by using the Lagrangian equation. That means you can see we can apply the Lagrangian equation to the simple pendulum, and from that one we will conclude that the motion of the simple pendulum is the simple harmonic motion. So if you have any question, you may please ask. So if I summarize the lecture, we found that in the beginning I have derived the expression for the D'Alembert's principle, that is summation goes from I to n fi minus pi dot delta ri is equals to 0, and then we have derived the most important expression for the classical mechanics, that is the Lagrangian equation, that is dou L by dou q dot minus dou L by dou q into is equals to 0, where L is the Lagrangian function, and that Lagrangian equation that has been tried to specify the motion of the particle, it may be applied for the different motion. And the first application we have seen that how this Lagrangian equation can be used to show that the motion of the simple pendulum is the simple harmonic motion. So thank you for joining me for this period. If you have any question, you may please ask, or till that, thank you. Have a nice time.